Hello everyone, welcome to Overflow. In this video, we'll discuss another LeetCode problem, that is the two sum 4 input in a BST binary search tree. So this is an easy level problem, and we'll understand how we can solve this question easily and how we can find a solution to those kind of problems. Okay, so there can be multiple solutions that we can end up with, but before moving on, make sure to subscribe to Overflow for regular LeetCode videos like this. So the question says, given the root of a binary tree, so they have given the root of a binary search tree and a target number k. Fine. I need to return true if there exists two elements. If there exists two elements in the binary search tree such that their sum is equal to the given target. Okay. There is two different elements from the binary search tree having sum equal to our given target. Okay, at target number k. So if the sum equals to this target, then we need to return true, else obviously return false. So this is the target. So that was the, if you remember, that was somewhat the question we had for our two sum problem, right? But here it's in a binary search tree. So the first question is how you should solve this. If you just look carefully in this input and output, you will find that this 9 is the target. So we need to do, so what we can do, for 2 plus 7, 9. That's true. And I find it fine. Also, there can be 3 plus 6. Also, there can be a solution, but let's not bother about that. Once you find a solution, if there exist two elements, there's more than two elements also, but there are two elements, that is true. We're done with it. We're not finding out all the solutions. Okay, we're finding at least one should be there. So how we're going ahead in this? Say, in a binary search tree, everything on the left of the root are less than the root. Everything on the right of the root are greater than the root. Fine. So that's the binary search tree, and that's its definition is. Now, how we can go ahead with that? The first basic idea should come in your mind is that the in-order traversal of a binary search tree gives you an sorted list. Like if you sort traverse it in order traversal, then it will be 2, 3, 4, 5, 6, 7. So this should be the numbers that will come up to us one by one. So what can you do is once you are like traverse this whole list by tree once and like traverse it in order traversal, and then take each of the elements and add it to our list. Okay, create a list, and in that add it one by one. So that can be one solution. Okay, I'm talking about one particular solution you can go ahead with. Once you have a list in hand, then what can happen? Once we have a list, then we know the starting element is the lowest element and the ending element is the largest element. So once we have that idea in our hand, we have a list over here, then we know that we need to simply apply our two sum 4. That is the one we applied in our two sum question. So that we need to apply, we simply need to do something like we'll sum the first element and the last element. If the sum is equal to our target, we'll return true. If the search is like less than our target, we incremented the starting element. If the search is less than our, like if the sum is less than our search element or the target element, we'll decrement our like we'll like what I'm meaning is like it got confused, but what it is like, if the uh, item like the if the sum is less than our target, then we need to increment. Okay, and if the sum is greater than our target, then we need to decrement. So decrement will move the ending pointer backwards. We'll move the second last element, something like this. And if we need to increase the values, we need to move that. So what I mean is, see, 2 plus 7, we got 9. Say the value is not 9. Say we are considering that if 2 plus 7 is 9 and we need to increase the sum. Okay, we need to find a sum that is greater than that. So we will move from 2 to 3. See, it became 3 plus 7, that is 10. But if we need to reduce the sum, then we go move from 7 to 6. So that would happen 2 plus 6. That's like 8. Okay, previously got 9 and we got 8. So this is the way that it happens. So this is a one kind of solution, right? It is not that it's a slow solution, it is a pretty fast solution, but we can have a different approach to this solution as well. We can have some approach like we can traverse this list, okay, till we find a solution. Like what I mean is, what we are doing over is we are making it converting into a single list. So in that list we will find 2 and 7 first, and we'll first figure out whether this is the root value or not. fine, like the sum is that or not, but we could have find us in 3 and 6, but in that case we don't need to traverse the whole, like the whole height of the list, right? Or whole height of the tree. So in that case, what we have done, we could have done a DFS approach, and in that, from each node we could have made a search finding out whether we can find us element or not, okay, a target element or not. So that's also possible. So that might reduce our total runtime, but more or less the complexity remains. The main complexity is of order of height, okay, because the order of height. Now, in that, the another complexity may arise is like traversing through all the elements of our in our list, traversing through all the elements. So all the elements traversal will happen only if there's a false return. Okay, we've traversed the whole list, but that may happen in this case as well. So complexity more or less remains the same, but the issue is you can find a solution before itself, like 3 and 6 could be a solution for element like 9 over a target, but we actually found out 2 and 7 and we return true. So let's see this solution. Uh, let's see this first solution of converting it into an proper list. What do you say? Converting into an First we converted into a list and then we got it. So what we did first, we took a list nums, fine. And in that, what we are doing, we simply went called in order and we passed our root, that is the root, and then the nums. So what we did is like in the in order, we either root is null, return, and then simply in order traverse the root left. Then when it comes to root val, we just added it to our nums, and in the traversal right, root right, fine. So that's the traversal we did, and then we went ahead with we returned over here, and then for each of the like I equal to 0, and there's another pointer like j equal to nums dot size minus 1, that is the last name in the nums, and we're doing I less than j. Okay, so that's what we're doing. And in that, if nums I and nums j is equals to k, that is we found two elements whose sum is equals to our target sum, we return true. And in the else case, if nums I plus nums j less than k, that is we need to increment our starting pointer I plus plus, else j plus plus, fine. So that's what we did. And after the whole loop, if we didn't return true at any point, we will return false. Okay, so that's the point that comes up over here. So first of all, let's just run the solution and see how quick or fast it works. Okay, so over here you can see, like, let's just run this. Yes, runs around 6 milliseconds, and previously when I did it was around 4 milliseconds. Fine. So that's what it runs. So we can have a different solution. I'll show you a different solution over here at once. So let's quickly write another solution. It is this and write another solution. So this is another solution that we can have over here. But let's see how fast or better the solution is. Then I will explain you how this solution works actually. See, over here, if you just look, it's like 3 milliseconds. You can see like the time actually got halved. Okay, so what the solution is here, we are not using a different list, but rather we're directly going ahead with the exact binary search tree we have over here. So first of all, we have this find target having root and the k. So we call a DFS function with root being given as two values, fine, and the k. Now this is our DFS function. Let's understand this. So in the DFS, we named it as two different nodes. Okay, one is root and this current. And we're checking if a current is not is null, okay, then return false. Okay, by any chance, if a current returns to null, we'll return false. That is, we couldn't find a solution. Okay, and else in the else case, what we are doing like in the return part, we are doing three things. What we are doing, see, we are doing an OR operation of three function calls. In OR operation, if any of the function call returns as a true, then the whole operation will return as a true. So that's the why our OR operation. Okay. So what we did, we called a search function over here. In that, we called a root, we called a current, and what we did, whatever was the target, being the k, we made it target minus current val. So current dot val is like we're subtracting target. So what if we had 5 in the beginning, right? We had 5 in the beginning. So what we did, target minus current val is 5. So target was on 9. So 9 minus current val is 4. So we are initially passing 4 to our root, fine, to a search. Okay. So what it will happen is, see, we'll actually look for 4, whether 4 is there in our list or not. the first search is. Once we find 4, our search is over. We got a true and we'll return true. There's no point going for other left, right, anything, right? We first call 4 as our target being it to search. So we called a search. Now we're checking the root is null. No, root is not null. We are not returning first. Then we're checking the root val is target. Root val currently what we send, root is the current root being sent. So what the root val is? Root val is 5 itself. Is it equal to target? No. Obviously the other part is not needed. So what we did, the target is greater than root val. Target is 4, root val is 5. No. So we are going for the last case. If the target is less than root val, yes, target is less than root val. So in that case, what we need to do, search. We are again calling search with root left being 3. Fine, current and target. So again, root is not null. So root val is target. No, 3 is not equal to 4. Then if target is greater than root val, yes, 4 is greater than 3. Then we are coming up to this loop. Then we are doing search root dot right and current and target. Right now we're moving root dot right. We came over here. Fine. Then we're checking for root null. No, root is not null. Now we're checking root val equal target. Yes, root val is 4 and target is also 4. And we got the current is not equal to root. What is the current? Were we traversing a current anywhere? No, current was holding this position only. Fine. So current is not equal to root. We traversed our root every time. We got root dot left, root dot val, but current was going on as it is. Fine. So current is not equal to root. Now we find that 4 is found. Once we found 4, we return true. True, true, true. No, you can see it's if you had it's a single equation is the OR operation. So once we find a true, true will return, and in the first case itself we return true. So what happened? We actually didn't traverse these elements. We actually didn't traverse this element. We simply found a value of like we found a value where the value is like true itself. Okay, so this is the approach what we are doing over here. Okay, so I hope this is understandable and it's pretty easy. Like it's like order of height of the tree. So that's what you are traversing and you're finding on directly. So that's how it is being done. So if you have any doubt or any problem related to the question, make sure to comment them down in the comments as well. I'll be happy to help you out in the comments as well. So thank you all for watching this video. Make sure to like this video and subscribe to this channel for regular LeetCode videos like